Hello, there's Katie. All right. Hello. She's at work or they're at work. They're at work. Okay. I'll be quiet because it's a work environment. Okay. Mm. And there's Chris, and he's always at work. He is a work environment. And there, what? Wait, and there's people cut. Wait, I'm totally. And oh yes, good afternoon, Kate. I can be like, yes, good after. All right, I'm going to start with good afternoon, Emily. Good afternoon, Michelle F. Oh, oh my God. All right, good afternoon, Jada. Good afternoon, Freddie. Yeehaw. Oh my God. Wait, that's so confusing. Oh, I get okay, Michelle Q. Michelle Q totally pulls it out of the end. And I actually just confused the Michelle F drawing with the Michelle Q, but I get
Say
it.
hi, Shy.
Oh, whoa, that's all right. And there's shot. Yes, okay. This is exciting.
It
All
won't
right.
load.
We just got food.
Come on, let me in.
That's it. Oh, let me in. Wait a minute.
Let me in. Let me
I'm letting
in.
you. I'm letting you in. Oh my God! Wait! Don't yell! Don't yell at me! I can't take it. Wait! I can't let you in. Wait! I'm trying to let you. Oh, there. Okay. Okay. There's. Okay. Okay. Wait. Let me go back to like the Michelles weren't confusing enough. Hold on a second. Let me go back, and then like Katie and Chris actually doing work. I mean, being. I mean, okay. Good afternoon, Stephanie. Back to that. Good afternoon, Brooke. Good afternoon, Victoria. Good afternoon, Fariel. No, no invite. Wait, no invite. Wait, Victoria. Wait, that's hilarious. Oh, okay. Victoria totally comes out of the shell today too. That's awesome. Okay, yes. I mean, oh, what did you get? Okay, Michelle F. Okay, guys. Good. We're back to, I see we've become ourselves again. Good afternoon. Boy, are we comfortable. Good afternoon, Yavi. I mean, sorry. And wait, is Yavi with the food? Okay, I'm going to stop. Good afternoon, Shy. To the food. Right. Victoria, don't get oh, crit. Oh my God. Wait, but Victoria. Oh my God. Craziness is it's a barbecue. I actually went to Dallas barbecue last night on 165th Street, like and St. Nicholas. No joke. Okay. You should. I did. Oh, wait, they're different. All right, we're having a stream cross. Alan is here. Hello. Okay, I should. I did. Okay. And there's wait, Chris is Shy. Shy is Chris. And we were all together in the Yellow Submarine. Okay. Um, Michelle. Yeehaw. Okay, I'm gonna remember the yeehaw. All right. Well, and good afternoon, Alan. Yes. Oh, wait a minute. Alan just said afternoon with no adjective. With no adjective. This is the last opportunity for Maria to give us an adjective to modify the kind of afternoon it is, and yet Maria is not here. That is, why? Okay. Maria has a friend in a high place who just totally like gave her a shout. Okay, her Wi-Fi is being wonky. Um, Wonky, meaning that it works in a chocolate factory? No, I get it. I get it. Okay. 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 So hello, everybody. So yes, this is our last, right. We're all exhausted, by which I mean I'm exhausted. I'm sure you're exhausted. Hold on, let's turn on the right. Okay. Um, oh, wait. Oh my God, Michelle FG. Wow. Okay, well that and then oh, it's weird because even though we can see Michelle in the chat is still her avatar, the Michelle as a cat thing is like in the chat. Okay. Why? Like, this is not interesting to you guys. Like, I'm like, oh, and then like, wow, we could go on the internet and like actually communicate with each other. Ugh, I am my grandfather. Okay. Uh, do you know? Oh, wait, I am going to say this since we are wrapping up. Do you know? Like after semesters and semesters of everybody using Chat P, cheap, what is it? You know, Chat GB. You know what the heck is it called? Chat GBT PG whatever the AI thing is that everybody. Yes, that right. Thank you, Alan. So like obviously everybody in the world uses that to cheat and blah blah blah, and we all understand this. Yes, but finally somebody showed that to Yeah, I should be put out of my misery. You're right. I should just go back to physics. Okay. But I will say that recently, finally, like another person from my generation, some creaky old, attitude was like, you got to see this. I'm like, I know about all this. I know everybody uses a cheat. I don't want to see it. I don't want to deal with it. And they're like, no, no, seriously, look at this. Like, watch. And like, they brought me over to chat to, and they were like, watch. Write a recommendation for this person to get a physics job with you. And then like, of course, the thing totally did. And it was like mind blowing, except it wasn't, because I knew it was going to, because I've been hearing about that for a year, whatever. But then the person to me was like, no, now give it a challenge, give it a challenge, like anything you want, just like challenge it, just be weird. So I go, yeah, I believe it. I know. I mean, we're not even going to have that discussion right now, but I literally said to chat my first challenge to, because I understood if I said like write an essay about electric fields, like I understand that it can do that. Like, and yes, that's scary and impressive, but I just decided to go for broke. So I was like, oh, that's funny, Alan. Oh my God, Al. Wow. Okay, that's funny. And meanwhile, it turns out like Alan is a bot in the first place who just made that joke. But no, that's very funny, Alan. But you know what I said to Chat, just thinking like, all right, I'm just gonna be, that's funny. Okay. I just said to Chat GPT, I was like, fine, fine, fine. Okay, write me a knock knock joke about aardvarks. And it totally did. I mean, it literally, I mean, it was the worst joke ever. And like, it only made sense as a joke if you assumed like some sort of thick, like Russian accent or sorry, no offense, but like, it only made sense if you assumed an accent, because otherwise, but somehow the minute the joke came out, I understood that's what you were supposed to do. I mean, I'm going to tell you, I mean, it's so bad, but it came so fast and it does work as a joke. It was like, knock, knock. Who's there? Aardvark. Aardvark who? Aardvark a mile for a party, but all they're serving to eat is ants. Like what? Like that actually worked. Okay, anyway, that impressed me. Like now, like I do understand that it can do physics homework if it can do that. But okay, I'm gonna give, all right, all right, all right, all right, all right. So we actually have to, okay, so we have to wrap up this semester here. We actually do. So First, I think we took care of most of the bookkeeping, right, last Monday. Like, honestly, I know it's weird, but we're going to do physics today. I'm not really going to teach you 85 million new equations or ask you to solve 85 new problems. Like, I'm not crazy. Well, okay, not in that respect, I'm not. But I am going to, there's no Wi-Fi. Well, that's classic. All right. What I want to do today in the final class, and I always do this in the last class, especially like now that you've slogged through physics for 2 semesters, and really honestly, it really has been terrific having you for 2 semesters. I want to try my best in the last class to sort of give you what I think is the point of this material, like what it means in the physical world in the end. Like I do want you to pay attention once I start rolling. And I do want you to try to get it. Like there's not a million notes to take down or a million equations or a million procedures to follow. But I want to try my best to have you try your best just to see how the general story of this physics material fits together and says something about the world. Okay, like I actually am serious now, or I'm going to be getting increasingly serious. Um, so so one of the reasons I like to have all the loose ends tied up before we do this is so that in the last class, I try to make a little sense out of physics, okay, or this physics. So we're gonna, and I'm gonna try to explain what this equation on the board, this last one equation means. Again, you're not gonna solve problems with it. I'm not gonna like quiz you on it or anything, but I just want to give you one last equation that I think ties the material together, and it is a true equation, and it is the one on the board right now, okay? So in a minute or two, I'm going to start finishing the physics for you. And I, as I sometimes do, I will kind of talk loudly and I may start talking a mile a minute and just bear with me once I get rolling. And again, like, oh, and so, so let me type a couple more loose ends to make sure. Like once I get going on the physics, then I'm just going to get going on the physics. I'm going to hope you're paying attention. I'm going to hope you get it. I'm going to hope it says something to you. And then when I'm done, when I get to what I think is the physics punchline of all this, then I'm just going to cut out. Like I think I've done once before. Like I'll just be like, bye. And that will not be later than 1:30. It might be a little bit earlier than 1:30, but whenever I think I'm done, I'll just be like, I'm done, and I'll just shut down, and you'll shut down. And hopefully I'll see you all on the other side in one way or another in my office next semester, or when you hopefully come asking for letters of recommendation to other programs or to summer programs or to graduate school or to jobs, etc., or to come back and work with me in the physics program or in the lab somehow. Like I would love that. Like hopefully I've already made that clear. But you really have been a terrific group, and I really will miss you. And I hope that you all get really good grades in the end. And there's no reason to stop any, it's still possible for any of you who's still paying attention. But so again, to take a drive up to Maine, right? Okay, fair. Please do, please do. Excuse me. That's right. I forgot that you. Oh, come. Yes, no. Please do come to. Oh, I'm looking at the chat. Yeah, well, sleepover. Well, now it's getting awkward. Hold on. You might not see me. That's funny. Okay, wait. I'm looking at the chat. Oh. Wait, I'm looking at the chat, and I did just notice the Maria mic drop. I get it. We actually were talking about that before Maria's Wi-Fi like kicked in, but whoa, there's the adjective. You are killing me. Yes, but that in a good way. Well, you're killing me about the no. I'm noting the Maria adjective. I'm also noting that if anything similar happens to, like when I'm doing the whole physics thing, if it turns out by any strange stretch of the imagination, if by somehow in some background, what do you call it? Like Discord or or like WhatsApp group or something that you might have, like if in the background you arrange to, I don't know, maybe show like 100% videos, like just like last semester, you, especially today, if you were to do that, when I'm talking about physics, you would definitely all get whatever it is, 42 points or whatever that portal might or may not have been posted for. But anywho, yes, right. You're getting the hit. Right. Oh, yeah, I know. Wait, Michelle Quasman. Oh, she has. Oh my God. Okay, well, all right. I mean, if she can do it, guys, like seriously, and if Maria can give an adjective, and if Alan can claim that he's never heard of ChatGPT, I mean, okay. Well, it would be even better if you did it while I was talking about physics, but okay, I won't stop you either way. Okay, but all right. So the deal is this again. Alan invented. I believe it. I believe actually that ChatGPT invented Alan, actually. But okay. Again, once I get rolling, I'm actually going to tell you something about physics, or I'm going to try. Okay. And that's, and I apologize for that, but it's like sort of my job occasionally. So before I get into the physics, the last physics, let me remind you a couple of things. Like, as you know, I think at this point, the final exam will be posted tomorrow night, no later than 8 p.m. It'll be due back no later than midnight next Monday. Again, you can work together, but in the end, don't, you got to put down your own thing. Don't, don't believe the hype just because everybody says something is right doesn't necessarily mean that it is. Or even if freaking Khan Academy or ChatGPT says something is right, doesn't mean that it is. But anyway, blah, 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 you get all that. Again, if there's any questions or concerns about grades or anything like that, I mean, I think we, then reach out to me by text or by email, and we'll do our best to like make sure you're okay. Or if there's problems, hopefully that's all clear. The one last thing though about the final, like, yes, it's going to be shorter than the practice exam for the final, and yes, you'll have choices. Just to be clear, the reason that there's usually a true false, like there's usually a true false section, as I mentioned on Monday, on the final, if you have a true false section on yours, it'll be a choice. It won't be it'll be one of the choices. It's a tricky choice because in a way it's simpler to do true false than to solve a lot of problems. Like I know that. And it is true that if there's a true false section, yeah, for that section, you don't have to show work or do 5-step method or anything. Like it is simpler. But if there's a true false question, it won't be the questions that you see on the practice final. It'll be questions based on what I'm about to talk about for the last like hour of this class, right? It's there to sort of like be the one way to enforce or encourage you to sort of pay attention to the last concept of this class. Okay, so there may or may not be a true false section on your exam. Again, if you really want to prepare or study or be not surprised, like the rest of the practice exam is a better indication of what to expect. But if there's a true false section, then yes, you don't have to, if you choose it, you don't have to show work or anything like that. It is simpler to do, but it's not necessarily easy because you would have to sort of assimilate or get the larger concepts that I'm going to talk about for the next, like for the last 45 minutes. Okay. So it's like, it's not meant to be a trick. It's just meant to be a recognition that at the end of the day, physics can be tricky, and good luck finding the answers to this on ChatGPT or whatever. Okay. So ChatGPT hasn't rung yet. Fair enough. Look, fine. Like, so consider it a challenge. Now again, I'm not promising that there'll be a true false. Honestly, it depends whether I have time to write one or not. I mean, they're easier to grade, but they're harder to write. Hold on. Okay. So in a minute, like I say, I'm going to sort of shift gears and get sort of serious. I mean, hopefully I'll get like excited and hopefully it'll be interesting, but it will be serious. Again, once I'm rolling with the physics, like if it turns out that you all do show video during it to show that you're actually paying attention, I will be thrilled. And yes, you'll get the points for that. Like no joke, but I may not stop and make a whole bunch of jokes about it or anything. Because once I get rolling, I will want to get this concept out. Like, okay, that's why I'm getting this all out of the way now. And again, once I get rolling on the physics, then I'm going to do the physics and then I'm just going to shut down in sort of an anticlimactic way because it gets awkward for me. So I'm saying goodbye and thank you and congratulations and all that. Now I'm reminding you again in the chat. Oh, wait, I'm going to remind you in the chat again how to reach me if you have a, like obviously by email, or if there's a crisis over the next couple of days, you can reach me this way. Right. Okay. I probably will be in my office next week, but that won't help you in time for the final. But I mean, it won't, but I probably will be there if anybody's around or before people graduate to say goodbye, whatever. Okay. So wait, so I'm just looking in the chat right now. So before I start rolling, also, it may be difficult for me to know if you all show video, but I'll try to know. Deionized water. Okay. So before I shift gears into sort of serious mode, is there any last, like not personal confusion, but just general unresolved confusion about anything I haven't answered or anything that you don't know how it worked? Like, is there any that's not nice? Wait, what I said is not nice, or what someone deionized water is not nice. Yeah, no, fair enough. Okay. Um, is there any last like issue that relates to the whole class of like, wait, I don't know when the final is, or like, wait, I don't remember when grades come out. Well, actually, I don't remember when grades come out either. But is there any last question that I can answer for anybody that is not a personal question? Is there any last? I'm gonna wait for a second. Okay. In fact, I'm going to do the flip thing. Again, I'm watching the clock. We will not go later than 1:30. We will hopefully go a little earlier, but I am watching the clock. But let me do the flip thing. Before I shift gears and do physics, would you just raise your electronic hand if you basically feel like the expectations for the next week are clear? Like if you know what it is you're supposed to do or what's going to happen. Okay, cool. Okay, cool. Thank you. Okay, awesome. Oh my God, oh wait, people are showing video. Whoa, I am noticing like, hello, Victoria, that wow. Okay, and Michelle, okay, wow, if you all show, okay, and there's, okay, cool. Okay, okay. Again, if it does happen that, if everybody's gotten the hint, if it does happen in the middle of this, that literally every single video goes on, even for a minute, I will note it and you will all get to 42 points. Like, no, but I might not stop, but I'm saying that, maybe I will, but okay, just saying. All right. Okay. So, whoa. What? Wait, is that even a thing? Okay, wait, I have to say, you can't do, wait, I forced an A. Okay, that's hilarious. But if you could do that, you could force an AI to give me 100K subscribers and let me retire. So what people do, wait, but what's even the point of that? I don't even get why would you want it to get, Okay, well, all right, I don't even. To generate new stuff from it. Oh my God. Okay, interesting. Well, I mean, for all that matter, you don't know for a fact that I'm not a bot, I guess. But really, like, would anybody make a bot like this? Okay. Um, oh, okay, okay. Okay, weird. Okay. Um, okay, weird. You're gonna put you on a list. Okay, okay. Um, so okay. So here I go. Like physics. A, I want to remind you this course sort of divided into three big topics. The first topic was simple harmonic oscillation. The second topic was waves. The third topic was fields. The thread through the whole course is that all the simple harmonic oscillation stuff, all this like mass going back and forth on a spring and all of this math that goes with it is some abstract math that is really important, as it turns out, for like PChem and instrumental, and for going on, if you go on to any field of like of physics or math or subatomic chemistry, all that math and all that simple harmonic oscillation stuff is really important. But more specifically, the reason we did all that simple harmonic oscillation stuff, just to remind you, is the idea is that if you really understand well enough what happens when one actual thingy thing goes back and forth cosinusoidally in time, then if you put together enough of those simple harmonic oscillators, if you put together enough of those thingy things, those particles, and you arrange them so that they're oscillating cosinusoidally, harmonically in time and in space, then you create this thing called a wave, right? I mean, that was the whole point of question 4 and the last exam and all of that. The whole reason we study oscillation so intensely is because if you put enough oscillators together in exactly the right way, or if nature puts together enough oscillators in exactly the right way, what you get is this thing called a wave pulse, rippling through the medium. You get, if you create a medium, if you create a collection of properly oscillating material particles, you will get an immaterial pulse propagating, flowing through this material medium. And that immaterial pulse is what we call a wave, right? So remember, and a classic example of that is a sound wave. Remember, sound waves are an example of something that really exists, that's really scientific, that's really part of nature. Something that a sound wave is an example of something that really matters in space and time, but isn't matter, right? I'm not like trying to be cute. I'm trying to be a little cute, just like you remember the concept. But what I'm really trying to say is that the big heart of this course, waves constitute a big example, particularly sound waves, constitute a big example of the heart of this course, which is to say that there is stuff flowing through space and time that really matters, but isn't matter. That there is that a deep reality underlying the material world, the physical world of science, right? A deep reality underlying the physical, material, tangible, touchable, countable, massive, discrete, separable world is immaterial, non-touchable, abstract, non-massive, non-separable entities for such as waves. And these entities, like, they make a difference in the real world, but they're not physical matter. They're not material, right? And that, to my mind, that's already kind of interesting, that something that really is making a difference in the material world is itself not material, right? Like, you can't touch it, you can't separate it, you can't feel it, but it's there. What is it? What are waves, sound waves, an example of? They're example of raw information flowing through space and time, right? Like, what do I mean by raw information? I mean numbers, right? Like remember the whole Doppler effect and all that stuff. Like, why is it all important? Why do I make such a big deal of these like detailed Doppler effect problems? Because at the end of the day, remember, if I sing, or if I even say like one note, like the note A, right? If I vibrate the air molecules in the air such that your brain hears a note A, what has happened? What has gone from my mouth to your ears? Well, the only thing that's moved ultimately is air molecules. But as we've said many, many times, no air molecule has gone from my mouth to your ear, right? When the note A, the middle A on a piano, or the note C, whatever, when the note C goes from my mouth to your ears and ultimately it gets registered by your brain as the note C, what has happened is that air molecules outside my mouth have vibrated back and forth, oscillated back and forth at well, if it's the note C, at 256 times per second. And then they go through the air, through the medium of the air, and then hit your eardrum, and your eardrum vibrates back, a totally different medium, vibrates back and forth at a totally different speed, but at the same frequency of 256 cycles per second. And then an electrical signal goes through your brain, totally different medium, totally different speed, totally different everything. Like no longer air molecules, no longer ear cartilage, now like electrons or charges going back and forth at what? 256 cycles per second. And eventually your brain registers that as, oh, that was the note C. So what is it that I've sent from my mouth to your brain? Ultimately, I've sent the number 256, right? Like that's what I've sent. That's what's traveled in a real way through the world, is not a thing, but like a number. That's the one thing that's been preserved through that entire bizarre journey of oscillation of this medium, oscillation of that medium, oscillation of that medium. What's carried through, what is the real entity that has made a journey from my mouth to your ears is a frequency, is the number 256, if it's like the note C, or the number 440, if it's the note A, or whatever. And then it's like I'm saying a bunch of words and saying that it's a whole bunch of numbers all together at the same time. But what it is numbers. Now, I don't mean numerals, right? I don't mean, sorry, I don't know what three. I'll have to answer that at the end. Or text me. Sorry, I'm sort of vaguely noticing the chat, but I may not be able to answer the chat while I'm talking about this. But what was three? You might want to email me or text me about that. What I'm trying to say right now is that waves are an example of something that's real, that's moving through space according to the laws of physics, but it isn't material. What is it? That when a sound wave moves through space and time according to the laws of physics, what is moving through space and time? Numbers. Right now, I don't mean numerals. Like, I don't mean like symbols. I don't mean literally the digit 440 is like going through space. I don't mean, it's not like Sesame Street. I don't mean like styrofoam, like symbols that look like Arabic numerals or Hebrew numbers or Chinese. I don't mean numerals. I mean numbers, right? Like the raw information. Now, the way we picture and represent numbers is with numerals, but that's just the way we picture it, right? That's the way we write it down. I'm not saying the universe knows the symbols for 40, but I'm saying somehow if I sing the note A and you hear the note A and you know it's the note A, what's gotten to you somehow is the number 440, like cycles per second. So that's raw information, travels through space in the form of waves, right? So that's our first big example in this class. And how are they made? They're made from a bunch of material particles oscillating harmonically in a very specific manner, right? So again, stay with me here. I'm saying we had to learn exactly how thingy things vibrate, oscillate in a specific way so we can ultimately understand how non-thingy things can arise as a true part of science and nature, not as a fiction or a science fiction, but as a science, right? And the deal again is, remember, sound can exist or flow through the world. The immaterial sound of numbers can flow through the world as long as there's a material medium through which the immaterial pulse can flow, right? In other words, again, I can make a sound right now in a room because there's air in the room to vibrate in a certain way. Air is not sound. You can totally have air and have no sound. Air isn't sound. But at the same time, air is required for sound. You can't have sound without something like air or water or guitar string or something to vibrate the air through. Like there is no sound in outer space for that reason, right? So again, I'm just saying the one big conceptual takeaway to get from the wave portion of this course is in order that a wave is a wiggle of information, but in order for there to be a wiggle of information, there must be actual things wiggling in a certain way, and those things are called the medium. Okay, so that was like the middle part of this course. Okay, then we got into fields. What are fields? Fields are apparently the idea of just raw information just sitting around in space. Like, right? Like a wave was raw information flowing, traveling through space and time. But a field, like an electrostatic field or a gravitational field, was this idea that the minute you have anything in the world at all, like the minute you have a point mass in the universe, or the minute you have a point charge in the universe anywhere, then the information describing, wait, was 3 field? Yeah, 3 is field. Yes, 3 is field. Yes, exactly. The minute you have a point charge anywhere in space, then automatically, we believe, everywhere in space, you have information describing the vital statistics of this point charge. Like if there's a proton over here in the universe or in a lab, we believe apparently that everywhere through the universe, there's a bunch of information describing how much charge this proton has and where this proton is located, right? Now, again, we believe there's this raw information now just sitting everywhere in the universe, sitting in what form? Sitting in the form of vectors, right? Or if you like, as we mentioned on Monday, or you can connect all the vectors up in your mind and call them field lines. And that's described more in the 2 last videos that I asked you to look at like last week or whenever we had asynchronous time. Now, again, let me make this clear, this idea of fields, or as clear as I can for right now. Whether you're talking about vectors being everywhere in space or field lines being everywhere in space, remember, these are representations, just like numerals are representations of numbers. Vectors and field arrows and field lines are representations of raw magnitudes and raw directions sitting everywhere in space. When I say that there's a field somewhere in space, I don't literally mean that there's literal like styrofoam arrows sitting in space or literal like plastic lines running through space. I don't believe there's literal vectors or literal lines any more than do I believe that when I say the note A, I don't believe I'm sending digits to your brain. But I believe that I'm sending information to your brain when I sing the note A or when I say anything, right? Like somehow data, not numerals, not written symbols, but numbers, numerical information is being sent to your brain when I make sounds. Similarly, when I put a proton anywhere in the world, there's numerical, directional, and magnitudinal data that gets spread out everywhere in the world, describing how charged this proton is, or how massive this proton is, and where it is, right? So this is the notion. So waves were raw information traveling through space and time. Fields is raw information sitting in space. Now, again, with waves, we believe that the raw information travels through space because a bunch of material things in space oscillate together in a specific way. So we're not like just making up magic. We're not, right? We're saying we believe that non-material information can ripple because there are material things that are rippling. But then fields are just raw information sitting there in space. Now, why do we believe in that? That seems almost harder. Like what's going on there? What's our evidence or our desire to believe that? Well, let me start by saying, remember, the notion of fields in the first place comes from certain forces like the gravitational force and the electrostatic force, forces that seem to be acting through a distance, right? Like we don't believe in fields when it comes to friction. Like we don't ever talk about like a friction field or the normal force or the tension force. When we're talking about forces, one thing pushing another by touching it, then we don't have any notion of fields at all. Then we're just like, oh, like the friction force, one block pushes another block by rubbing against it. Okay, there doesn't have to be any like intermediary or medium or anything there. But when it seems to be the case that the sun can pull on the earth through empty space just as easily as the sun can pull on the earth through whatever happens to be in the way in between the two, like whether there's a moon or Mercury or something in between the earth and the sun, doesn't seem to be necessary or helpful or hurtful to the sun's ability to pull on the earth toward it. Same thing with protons and electrons. They just seem, and electrons and electrons and protons and protons, all those things seem to just push and pull each other automatically, whether there's stuff, whether they're touching or not, whether there's stuff in between or not. These are called fundamental forces, actions at a distance. Now, this idea of action at a distance originally comes from Newton, remember. And I want to tell you quickly that when Newton came up with this idea that like of F equals GMM over R squared, that for any two masses in the world, any two masses in the world automatically pull on each other over any separation at all, distance R, and the bigger either one is, the more they pull, and the closer together they are, the more they pull. When Newton came up with this equation, GMM over R squared, and decided that it applies to all objects of all mass anywhere throughout empty space, this was a controversial idea, to put it mildly. And at the time that he came out with this idea, Newton, just like Newton is the hero and the intellectual giant for many of us today, Newton has had his heroes and his intellectual giants and his teachers. And you don't hear about them as much in science classes, but one of Newton's major heroes was a great teacher at the time called Sir Richard Bentley. And Sir Richard Bentley was like a don at Cambridge University, and he was an expert that many of the younger generation turned to for advice and for tutelage and for math and science, advanced expertise. So he's like, he's like an OG. I mean, you don't hear about him today, but this man's name was Sir Richard Bentley, and he was like teacher to the stars in the 17th century. Like, I'm not joking. And at the time that Newton's theory came out of F equals GMM over R squared, this idea of action at a distance, a physicist of the time, of Newton's day, wrote a letter to Sir Richard Bentley objecting to Newton's theory, because Newton's theory involved things just pulling and pushing on each other through empty space. And I'm going to switch screens for a second and show you an excerpt from this letter, which I did have on the screen a second ago. Hold on, I'm going to just show you. Sorry, no. Hold on. Okay, here we go. Yes, okay, hold on. So I'm going to switch screens for a second and show you something. Right, okay. So at the time, during Newton's day, there was a letter written to Sir Richard Bentley about this idea of action at a distance. And here's an excerpt from the letter. Okay, so again, this is about Newton's theory. This is from the 17th century, the early 18th century. And the letter says, among other things, it is inconceivable that inanimate, brute matter should, without the mediation of something else which is not matter, operate on and affect other matter without mutual contact. That gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else by and through which their action may be conveyed from one another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Okay, so this was written right at the end of the 17th century. This is a critique on Newton's theory written to Sir Richard Bentley, Lord Richard Bentley, at the University of Cambridge. Now, let me make this clear again. Like, look at this first. This is just an excerpt from the letter. But among other things, he's saying that gravity should be innate, inherent, and essential to matter. In other words, that something could affect something else. Yes. Okay. So Maria's got it. Yes. This is brutal. This is totally brutal. Like, if this were a modern day, I mean, this is a critique. In modern terms, basically, this thing is canceling Newton from the culture. I mean, literally, it's saying that gravity should be innate, inherent, and essential is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking could ever fall into it. Now, by competent faculty of thinking, they don't mean a well-paid set of professors. They don't mean competent faculty like that. They mean competent faculty, like ability, like capacity. So it's saying, right, this idea of action at a distance, this idea of like the sun being able to affect the earth without touching it is so stupid that anybody who's remotely competent or like at all like reasonable would never think this, right? And I'm not kidding. This is a real thing, right? And this is what somebody's, yeah, it's totally right. Wait. Right. Okay. You're totally with me. Good. Yes. This guy that's writing this letter is calling Newton delusional, saying that's moronic, dude. Seriously, like the earth is pulling on the sun without touching it at all through empty space. Like, really, yo? Really, bro? That's what this letter's saying. And I'm getting excited because it's real. I'm not joking. Now, here's the crazy part. And again, what this is saying is the idea that there could be somehow the earth affecting the sun without touching it, or later on, as we get more, same idea, a proton affecting an electron without touching it, like over vast distances. This letter saying, like, dude, seriously, that's moronic. Like, that doesn't jive with any. That's funny. Wow, Alan's on fire today. Okay, yes, right. He should. Oh, by the way, wait a minute. Am I looking at the thing? Are you? Oh, wait. Am I seeing? Oh no, almost there. Okay. So now here's the thing, though. It gets weird, and I'm glad you're with me. It gets weirder because the person that wrote this letter about Newton's theory, the person that wrote this letter to Sir Richard Bentley, and obviously the letter has survived, right? The person that wrote this letter was a famous physicist of the time that you've heard of. You actually do know the person that wrote this letter. Yes, right, modern day, right. Now, here's the thing. And obviously you get it. The letter is a scathing critique on the idea of action at a distance. Well, the person that wrote the scathing critique, I mean, usually at this point I'll take, if you want to put guesses in the chat for a minute of like, I will tell you, you've heard of all of you know the person who wrote this letter. I mean, you know the name of the physicist who wrote this letter. Like, I'm not saying it's easy to guess, but it is guessable and it is knowable. You will have heard of the person once I tell you. Yeah, no, this is totally like an ancient day cancel culture thing, right? Oh my God. All right, wow. I'm going to get straight to the point. Someone in direct chat just made a joke, like a weird joke. I think it's a joke in the direct chat. Except to cut to the chase, I'm going to tell you that this weird joke that someone just, okay, it's a funny joke, I'm going to tell you what the funny joke is that someone just put in direct chat. It's actually kind of a brilliant joke. Wait, I'll tell you the joke and I'll tell you the real answer to this in a minute. I just want to see if I can get one or two serious guesses as to who this physicist might be that said this. Wow. All right. Actually, people are guessing it in the chat. Wow. Okay. No, it's not me. Okay. No, it was like in 1693. But here's the deal. One person. Oh, wait. I think maybe have I told you this before? Because yes. Okay. No, you guys are geniuses. And that was a person put that in as a joke in the chat, a half joke. And then another person put, yes. Here's the deal. Absolutely. Yes. And maybe you knew this already, or maybe you just figured it out, or maybe like, because you know I'm crazy, I would like a thing like this. Yes. The person that wrote this letter was literally Newton. Yes. But it's not a joke. I mean, it's not a joke. Newton, and this is like the essence of scientific brilliance, in my opinion. And is it crazy? Yes, it is crazy. But the deal is, this is a turning point in the birth of classical science, because what happens is you have an individual who's looking at the world and saying, I'm trying to be so objective and so unbiased. I'm looking at all the data as best as I can, and I'm putting the data together into a model or into an equation or into a descriptive system that is making predictions that are working, that is telling me when the next eclipse is going to happen and when the next orbit of Jupiter's moons is going to happen, et cetera, et cetera. And I'm putting all together this data, and the data is saying that there's an equation called GMM over R squared that seems to say that everything else is pushing everything else or pulling everything else through empty space. But the person that came up with GMM over R squared, the theory of gravitation, the person was so objective and so unbiased when they came up with this crazy idea of action at distance, that then the person said, Newton said, it doesn't freaking make any sense. Like, the person was able to be so objective and so unbiased in the theory they came up with that they themselves could not see how the theory could actually jive with any presupposed notions of how the world should work. In other words, if you go into the world thinking you understand basic things like, for me to affect you, I've got to be able to touch you, or for me to be able to affect that object over there, we've got to be nearby each other. We've got to be able to make physical material contact. If you go into the world with this seeming basic bias that you don't even know is a bias, which is, well, for stuff to affect other stuff in the material world, it's got to have material contact. The only thing that can affect matter in the material world must be other matter. If you go into the world with even that bias and you don't even realize it's a bias, you would never come up with GMM over R squared. You'd never come up with gravity. Newton somehow gets himself so unbiased that he comes up with GMM over R squared and then looks at it and is like, that is freaking crazy. That does not even make any sense. But he publishes it anyway. And he secretly writes a letter to his role model, to his teacher. And he's like, so I just published this thing, but it's like totally freaking crazy. I don't understand it at all. I must be like idiotic to be believing this thing that I just published. But why did he publish it? Because the data is there and the predictions work. So it's so scientific that it's not even philosophically reasonable. That's where science starts becoming science. Newton literally in one part of his brain says, this crap works. And the other part of his brain says, this crap doesn't make any sense. But I don't know what to tell you. Like, I'm not a philosopher. I'm not it's not a religion. It's not even math. It's just like stuff that seems to be working in the world. Here you go, world. And later on in the letter, he basically says, I leave it to future generations to figure this out, why this is happening, how this is happening. I don't get it at all. But it drove him crazy. It is Newton who wrote the letter, and he did secretly on the side, but the letter survived, where he's basically saying my own theory makes no sense. But it's not up to me to decide what sense is. It's just up to me to be a scientist and say, this is what it is, yo. Right? That is crazy, but it's brilliant, in my crazy and brilliant opinion. Yeah, no, it is crazy. Oh, okay. Sorry. Ha! That's fine. They will have a wrap. Oh, that's funny. Okay, wait, I'm just looking at it. Okay, right. Okay, so the massive beef, look, the massive beef that was had at this point is Newton against himself. And that is true. He went crazy over this. Like, no, I mean, it drove him crazy because it was his biggest discovery, most important discovery of all time. And he knew it. He knew it was a huge discovery. He knew it was big. And we use the equations to this day to put like men on the moon, among other things, But what it implies now, to get back to the point of this course. But I am serious about this, right? Like, I mean, yeah, like that, the quote was Newton. And those of you who guessed that, good for you, seriously. You clearly are following something in this course to have guessed that, or whatever. I'm going to stop the share of that for a second and go back to something else. Now, wait, hold on. I'd love, yeah. Well, I'll take it. I mean, I should be so lucky. But now, where am I going with this? Oh, wait, are you all, hold on, I'm looking at the, oh, almost, not quite. Okay. So what's it? Oh, now, this drove Newton crazy till his, that's funny. It drove him crazy. Now, why particularly? Let me break this down. We have 25 minutes. What is so crazy about believing that like the sun can affect the earth without touching it, or that a proton? Because maybe now you're used to that. Maybe you don't think it's that crazy. Let me be specific about what drove Newton crazy about this. To believe that the sun can pull on the earth without touching it, or to believe that a proton can pull on the electron without touching it. Let's be clear. We're not just saying vaguely or qualitatively that the sun pulls on the earth. We're saying quantitatively, precisely, the sun pulls on the earth gmm over r squared, or a proton pulls on an electron kqq over r squared. We're saying that the exact amount of pull is numerically predictable, and then F equals ma. So is then measurable and seen in the acceleration that will result, right? Like you know, if you pull something, you accelerate it, right? F equals ma. So we're saying that the exact amount that the sun pulls on the earth is determined by exactly how big the sun and the earth are and how far apart they are, right? Right. In a predictable and measurable numerical way. Now, why is that so crazy? Because think about it then. If we believe these equations, if we believe gmm over r squared equals f, or kqq over r squared equals f, then again, let me repeat, because this is really important. It means we believe that the sun pulls on the earth with an amount of newtons that is specifically numerically determined by how big the sun is, like how massive the earth is, and how far apart they are. So if you believe that, now then just like play the movie out in your mind. The sun exerts a force, a gravitational force on the earth. And that's a pull. So then the sun starts pulling the earth like toward the sun. So then F equals ma. So then the earth, all other things being equal, will start accelerating toward the sun. So the earth, at least sometimes, would get like closer to the sun, right? Now, if you believe, and same thing with a proton and electron. So if you believe the actual numbers of gmm over r squared, that means that then, right, okay, cool. That means that then the earth comes closer to the sun. And then according to gmm over r squared, the sun must now exert a new magnitude of force on the earth because the r just changed. And therefore the F must change, right? So if you believe the data and these equations, if you believe the numbers, which is where the equations are coming from in the first place, it means that when the sun reaches out and pulls on the earth and starts grabbing it, and then the earth starts coming in, now the sun is going to generate a new different pull because there's a new different closer distance, right? Why is that a problem? Because that means that the sun must somehow know that the earth is closer when the earth gets closer. I don't mean that the sun knows consciously, like the sun, I don't mean, again, when I say numbers, I don't mean numerals. And when I say the sun knows where the earth is, I don't mean the sun is consciously sitting there thinking about it. I'm not being that weird. But I am saying, wait, if every time the earth changes its position, the sun changes its pull magnitude in response, that means that the new whereabouts of the earth must be somehow being sent to the sun in order for the sun to now create a new or generate or exert a new magnitude of pull. If the pull is based on the distance of the Earth, then every time the Earth changes its distance, the sun must somehow be finding out about that, right? And this is what, in other words, to believe in action at a distance is necessarily to believe that the information describing one object over here is somehow accessible to any other and every other object over here and over here. And every time something changes on object number 2, somehow object number 1 over here finds out about the change, the new distance or the new mass or the new charge or whatever, or all of them. So to believe in action at a distance is to believe that there is somehow information, that the fact that the Earth exists means that information describing the Earth must be everywhere in the universe, including wherever the sun is, right? Now, that's what Newton didn't like. Okay, that's what in modern terms we call a field. Newton didn't like this idea at all. Which means if you don't like the idea of fields, if you think I'm just like making this stuff up or it's just unnecessarily abstract or imaginary, you're in good company. Newton didn't like I didn't call them fields, but whatever the idea is behind fields that we are now saying, he didn't like either. And the specific reason he did not like the idea of fields, or that it not just didn't like it, like that it drove him crazy, is that he asked himself the question, wait a second, if somehow the sun gets the information, has the information of the Earth, every time somehow the Earth changes its vital stats, somehow the sun finds out about that, if that's what these equations mean, then there's only 2 possibilities, said Newton in his mind and in his letters. There's only 2 possibilities about these information updates. Either the updates are happening instantaneously, like right away, like immediately, like in no time, or they're not. Like there's only 2 possibilities. Either they are or they aren't, right? Newton said, wait a second. If every time the Earth moves or every time an electron moves, the proton like finds out the new location of the electron, there's 2 possibilities. One is that information of the new information of the new address of the electron, either that information is going to the sun at infinite speeds, right? i.e., it's getting to the sun right away. That's option number 1, right? That if the information updates, if they're getting from the Earth to the sun at all, option 1 is they're getting there right away. The information, the numbers, the vectors, what we would now call the vectors, the field lines, either they're getting to the sun right away. That's option 1. And Newton thought, well, that's crazy. That can't be. I mean, that it's crazy. Oh, I'm watching. Okay, fair enough. And again, if you do it, I will congratulate you and I will give you all the points, but I'm going to keep going. But so option 1 is that information updates, changes in the field vectors or the field lines, get from one place to another at infinite speeds in no time. Now, if that's true, and actually, well, if that's true, that means it takes no time for the Earth to tell the sun that it just moved. And if it takes no time, it means it doesn't matter how far away the sun is, that it takes just as long to tell the sun as it would take to tell Jupiter or to tell another galaxy. In other words, if that's true, then everything in the universe right away, immediately knows what's going on everywhere else in the universe. And therefore, distances don't matter at all. Like, it doesn't matter how far away you are. It still takes you no time to get the information from here to there. Well, that's pretty crazy, because that means the whole universe is just communicating with itself instantaneously all the time, which means it always knows what's going on all the time. So the future and the past and the present are all the same. Now, that's pretty crazy. And you could see why that crazy idea Newton didn't like. But he actually liked that crazy idea more than the alternative. The alternative, which seemed even more absurd to Newton, was, no, when the Earth moves, somehow its new whereabouts, somehow its new information update takes time to get to the sun. Like, the information update doesn't travel at an infinite speed. it travels at some kind of finite speed. The way like cars or rocket ships or other regular material objects travel at finite speeds. The other possibility is that every time the Earth moves or every time an electron moves, the new address gets sent everywhere else at finite speeds. Now, to Newton, that was even more absurd because, like, what would that speed be? What would that speed be based on? How would we know that speed? And it's got to be whatever it is. It might be a finite speed, but it's got to be pretty fast because the universe seems to be communicating with itself all the time. So Newton both of the alternatives didn't make sense to Newton. And he ultimately chose the first alternative, that the information updates were just happening instantaneously, but that was very unsatisfying to him. So he died unsatisfied with all of this and left it to future generations to figure out. Well, in the future generations, we did figure out some things. What we figured out. Right, sorry, well, fair enough, but I'm about to explain that more now. Here's what we figured out in more modern times. First of all what I'm just trying to say is, if you don't let it, I'm trying to put perspective on this whole idea of fields. I'm saying that the minute that a proton exists in the world, immediately vectors or field lines exist, but not necessarily immediately, but automatically vectors or field lines exist everywhere in the world. That's telling everywhere in the world how big this proton is and where it is. That's what I'm trying to say over and over about the idea of a field, is that a field is a sea of information that any one material particle creates throughout the whole world. If some material particle exists in the world, then it creates a sea of information everywhere in the world, declaring how big it is and where it is. If you think that doesn't make any sense, or that's weird, or you're wondering, like, why the heck would anybody believe in such a thing? That's funny. I'm saying the reason we believe it is because it seems to be happening all the time. The reason we believe it is because we're trying to be scientists like Newton and say it's not about what we want to believe. It's not about how we think the universe should be. It's that, look, it does seem like whenever the sun moves, the pull on the Earth does get affected. We can do the numbers. We can see the accelerations. We can predict orbits, and we can predict the motion of electrons through wires, call it circuits in the lab. It seems like these equations work. So the equations are saying that somehow the information of stuff over here exists in the world and affects stuff over there. That's the notion of a field. But with all the work that we've done in modern terms, especially as of 1879 with fields, it turns out a man named Maxwell in 1879, let me go back to the other screen now. Maxwell, hold on. Maxwell in 1879 put together all the knowledge of electrostatic fields and magnetic fields at the time and realized, hold on, I want to put the share back. Okay, here we go. Okay. Maxwell realized that when there was a change in the electric field over here, like because a proton moved or another proton or an electron joined a proton and it got bigger, so the charge got bigger or whatever, when something over here is creating an electric field, if something changed in the point source, in the source charges that was creating the field, then what happened was the vectors right near the charge would get bigger or change their direction or whatever. And then the vectors next to those vectors would get bigger or change their direction or whatever. And then the vectors next to those vectors would get bigger or change their direction or whatever. In other words, anytime you changed something that was causing the field, what would be sent out through all the field vectors or all the field lines was a ripple of some kind, that each vector would sort of change or vibrate or move in its place back and forth until the change got transmitted. The change in the information update would get transmitted through all the field vectors or the field lines. And that, in other words, Maxwell, in playing with the field equations of both electric fields and magnetic fields, did the math and realized in the end that whenever you changed what was causing an electric field, the electric field would change according to this equation on the board here, which you might recognize from earlier in the semester, right? Early in the semester, we had an equation very much like this. Instead of a capital E, we had a lowercase y in the numerators. But what this equation is that you might recognize is the wave equation, right? Only here we're using the dependent variable to be field instead of position. What Maxwell realized is that when you make a change in something that's causing the electric field, the update, the new information ripples out through the field in the manner of a wave. That is to say, all the little field vectors start oscillating harmonically one at a time in a phase staggered way, so that like this vector changes and then this vector changes and then this vector changes and back and forth. And so that what you get is a ripple effect or a pulse of the field vectors. And that ripple or that pulse of new information propagates through the field according to the wave equation. Okay? So this is where everything ties together, in my opinion. That in the modern terms, we believe that updates to the electromagnetic fields that exist everywhere in space, that updates to the information travel through the sea of information in the manner of a wave. What is a wave? Remember, a wave is a pulse propagating through a medium. In this case, what's the medium that we're now talking about? The medium is the electric field. What's the wave? The wave is updates, changes in the information of that electric field. Now, why is that interesting? Or why am I like ending the whole course with that idea? Because, well, first of all, as far as we know, it's true. And there's both, yes, Newton would have loved this. That's true. Or loved to hate it or something, but yes. Now, we believe this for strict, like there's strict mathematical proof, like demonstrations of this and strict experimental demonstrations of this, particularly called the Michelson-Morley experiment, which you could look up. I mean, we have more reason to believe this than we have to believe a lot of things. But the this that I'm saying that we now believe in modern terms is we not just that we believe in fields, we believe that updates to fields travel through fields in the manner of a wave. Remember that a wave is an immaterial pulse propagating through a medium, right? Like sound is an immaterial pulse propagating, flowing through a medium such as air molecules. The thing with this, though, is now we're saying, okay, updates to the electric field travel through the electric field in the manner of waves. Waves are pulses in a medium. But here's the weird thing. We believe in something like sound waves. We can believe in something as immaterial as sound because it's a pattern of, is it? Okay, thank you. Wait, okay, is that true? Oh, sorry. I believe you. I mean, sorry, because I keep changing my view. Almost, okay, I'll change my view. Sorry, because we have like 7 minutes and almost, okay. Oh, all right, very good. No, I totally see it. I'm very impressed. I do want to finish my point, but your timing is amazing, so it does mean that you're still with me. Thank you. I'm totally thrilled. I'm going to give you all the points. Yay, that's awesome. A great way to end 2 semesters. I hope you're not strangers. Okay, that is awesome. I totally get it. I'm totally appreciative. And it's perfect timing because give me like 3. Yes, no, I get it. I'm totally acknowledging. Yes, everybody's camera's on. That's awesome. You're totally all getting the points. I really appreciate it. And perfect timing because let me take like 4 more minutes of your life to make this final point now that all your cameras are on. But yes, it thrills me. Here's the thing. A wave is an immaterial pulse through a medium. An update to the electric field is a wave. So it's a pulse, an immaterial pulse through a medium. But the medium that we're now talking about is electric field vectors. They are already immaterial. When an update to the electric field travels through the electric field that exists everywhere in the universe, when the new information of where the Earth just moved to, or the new information of where an electron just moved to, when that travels through the field to get to the proton and tell it, oh, the electron's over here now, so pull harder or whatever, What's traveling is an immaterial pulse through a medium consisting of vectors or lines, or in other words, not air molecules. These things happen even in outer space where there's no air. Not water molecules. Again, these things happen even in outer space where there's no water. I'm saying that what pulses through to the universe to tell a point over here what has now just happened at a point over there, what's pulsing through is an immaterial propagation through a medium that already is just raw information. What's pulsing through is now a wave, an immaterial flow through an immaterial medium. That is very abstract. That's really weird. But remember, the equation that describes it, the wave equation, if you remember from earlier in the semester, the wave equation says second time derivative of dependent variable equals square of like omega over k, like constant of proportionality, times second space derivative of dependent variable. And if you remember from earlier in the semester, the thing in the parentheses, the constant of proportionality between the two second derivatives of the wave equation, that constant of proportionality is the speed at which the wave travels, right? Like omega over k or whatever. In the case of updates to the electromagnetic field, the speed at which they travel, it turns out, as of 1879, we know, is indeed c, the speed of light. What Maxwell realized in 1879, and I know we have like 2 minutes left, and we'll be done in time. What Maxwell realized in 1879 is, you could say on the one hand, that updates to the electromagnetic field travel at the speed of light. That's one way you could put the discovery, but the better way is to put it in reverse. What that really means, if you flip it on its head, what really Maxwell discovered in 1879 is not just that a certain weird thing travels at the speed of light, but that in fact, that is what light is. As you know, light is red light, light is violet light, light is also X-ray light, light is infrared light. Light is not just the visible colors that you see with human eyes. Light is anything that travels at the speed of light. What does it mean to travel at the speed of light? What is traveling at the speed of light is literally updates to the electromagnetic fields throughout the whole universe. What light is an update to the information describing something over here being sent to something over there. What light is a immaterial ripple in the immaterial medium of the universe's sea of information. What light is a piece of the universe over here telling a piece of the universe over there what's going on. What the speed of light is the rate at which the universe talks to itself. The speed of light is the speed of information. It is the rate at which the information describing what's going on at one point in space is communicated to any and every other point in space. The speed of light is the speed at which the universe talks to itself. That is the course. You've been awesome. I'm going to leave. I can't wait to see you in my office later. You'll all get the points for the video. I'll miss you guys very much, and please rock the final. Goodbye. Yes, have a great summer. Goodbye. Okay. Bye.